Hey guys, welcome back. Uh, Today we're going to go through and be talking about topic 1.5, atomic structure and electron configuration. If you're following along on this PDF, which I suggest that you guys do, you will cut through a lot of the stuff that you don't need to know and focus on the points that they're really going to be testing on. So if we go through and look at this, what we're going to be looking at here is what is an atom composed of, just understanding what Coulombs law actually is, and then talk about electron configuration. Note here that quantum numbers are not going to be assessed on this exam. I'm going to say this though, learn your quantum numbers. It's easy enough to know, and it's not that difficult. The last thing is talking about ions, basically ionization energy and what exactly is ionization energy. Let's go through and kind of talk about how an atom is structured. We talked about it before, but let's kind of go over this again. In the nucleus, in the center of an atom, you have protons and neutrons. Both of these guys have mass, approximately 1 AMU. Protons are going to be positively charged, neutrons are neutral charged. Outside of that, you have electrons. Electrons are have no significant mass, so we don't really count them whenever we talk about the mass of an atom. But they're going to exist out here in orbitals. So they exist out here in energy levels. This is a Bohr model of the atom, so it does include energy levels. We have 2 for the first one, 8 for the second one, and so on and so forth, moving up. Energy levels for electrons. You know what energy level you are if you look at the periodic table. So if you look down the period of the periodic table is going to be your energy level. For the first 2 here, this is going to be your first energy level. You have 2. Your second one has 8. Your third has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. 18 for your third energy level. Now I'm going to go over why I jumped down here in just a moment. So one quick and easy way of figuring out how many energy levels you have in an atom is by looking at your periodic table. Your periodic table really is the best cheat sheet you have in chemistry. So going back, we have energy levels of electrons, 1, 2, so on and so forth. This is going to be your basic structure of the atom. How do these guys interact with one another? The big interaction you're going to see here is what is this effective charge down here in the nucleus versus the charge on electrons on each different energy level. If you have a positively charged thing and a negatively charged thing, they're going to want to attract together. So they're going to be pulling closer together. Once things get too close, once these 2 electrons get too close together, they're going to start to repel each other. So that's why we have these different energy levels. First energy level is kind of the sweet spot in between the attractive force and the repelling force of these guys. We have those 2 things kind of working against each other. The attraction between the protons and the electrons, and the repulsion of the electrons pushing each other apart. So we do have 2 separate forces that are being played against here. The charge of the proton and the charge of the electron pulling each other close together. This is where Coulombs Law comes into play. Coulombs Law says that the force between 2 charged particles being pulled together, that force is going to be equal to the charge of the one thing, the charge of the second thing, divided by the radius squared. The 2 things you need to think about there are, what is the charge of the thing? In this case, the big thing for the charge is going to be how many protons do you have in your nucleus. That's going to be the effective nuclear charge. How many protons you have in the thing? What is this magnet like down here? And the other thing you need to worry about is the radius. In other words, what's the distance between the electrons and the nucleus? So the further out you are on energy levels, the less of a pull you're going to have here. Kind of think of it like with a magnet. If I have a magnet, here and here, it's not going to really attract very well. But if I bring them closer, all of a sudden they snap together because they're moving a little bit closer. That attractive force is stronger, and then it brings them together. The distance between the two things are important, and then what is the how big of a magnet do you have? In other words, how much of an effective nuclear charge do you have? Though that is the two big things that in a free response question you should relate back to. If they ever talk about intramolecular forces, it's going to kind of come back to the effective nuclear charge and the distance to the electrons. It's going to come back to those two things. I mean, let's go through, talk a little bit about ions real quick. When you're talking about ions, everything's kind of looking to get that octet. When you have an octet, you have 8 electrons in the outer shell. We'll talk about why that is 8 in a little bit. That may be stretching a little bit for these review videos, but in general, you want 8 electrons in this octet. If you have one extra one out here, that the distance between this electron and the amount of protons in here are going to be a little bit off balance, isn't it? We're not going to have a super strong magnet, and it's going to be far away. So if that's the case, this electron, there's not a whole lot of force going on this one little electron. And it's going to be really easy for it to fall away, get stolen, things like that. One analogy you can have is if I'm set to guard a certain number of things, the ones that are close to me, I can keep close eye on. If they're a little bit further around, that's fine. But if I have one that's in a building downtown, I may not check on it very often, so it's more likely to get stolen. That's one way you can lose an electron based on its intramolecular forces. So the other way, instead of losing an electron, if you want to gain an electron, why is it that these guys want to gain electrons so much? Well, it's because that the number of protons in its nucleus is pretty high. For chlorine, compared to the distance, this 1, 2, 3 energy levels that it has a large nuclear charge. So here we have a really big magnet in the center, and the distance is pretty small. So it's going to be very electronegative. It's going to be really electron hungry. It's going to want to get another electron. Another electron is going to pop into this place to kind of satisfy that, make the energy a little bit more stable. As far as ions, just a real quick reminder, if it's a cation ion, it's going to be a +1 charge. If it's an anion, it's going to be a -1 charge. One way you can remember that is for cation, cat has a T. T kind of looks like a plus sign, so it's a positively charged thing. Anion stands for a negative ion. We're talking about electron configurations now. Electron configurations have a lot to do with the energy level, but also what orbital the electrons are actually living in. Remember that the Bohr model is not quite right. The Bohr model had energy levels, but it's not just energy levels. They're also living in little orbitals, little suborbitals. The first suborbital that you're going to have is s orbitals. S orbitals look like a little sphere. P orbitals look like a dumbbell going in each axis, the x-axis, y-axis, and z-axis. And then d orbitals look a little bit weird. F orbitals look even more crazy. And then after that, you start getting into really weird geometries that are Lovecraftian in nature. We can describe these guys. So these guys are kind of like apartments. That's the way I kind of describe things. They're apartments. And if you look at this OffBound diagram, then you can see that it is kind of like a little apartment building. We have kind of the first floor apartment, second floor, third floor, so on and so forth. Remember that we have very lazy electrons that do not want to actually climb stairs all the time, and no one wants to live at the top of the stairs because there's no elevator in this apartment. The first floor apartment is going to be prime real estate. Additionally, no one really wants to have a roommate. If we can, we're going to fill up one electron at a time, and when we get up here to the suites with 3 bedrooms, each one wants to have its own bedroom. We're going to be using this OffBound diagram to go through and show what these electron configurations are. Electron configurations, remember, are just kind of the address of the electron. So to kind of go through and remember our electron configuration rules, one, off-bound rule. The off-bound rule is that electrons always fill their lowest energy level first. They're lazy little electrons that don't want to climb the stairs. So it's always going to be that lowest energy level, which makes sense from a non-allegorical point of view because electrons want to remain close to the protons. So they want to be in that first energy level. The next one is Pauli exclusion rule. Electrons do have spin. Don't worry exactly what spin is. I mean, there's graduate students in physics that ask, what exactly is spin? So don't worry too terribly much about it. Don't worry about it. All you need to know is that the electrons cannot spin the same way. So if one is spinning up, the other must be spinning down. So if they are sharing a room together and one's spinning up, the other must be spinning down in the opposite direction. And then we have Hund's rule. Hund's rule is the I don't like roommates rule. So each electron must fill an empty orbital before sharing an orbital. Also, one little note here is that electrons, orbitals, only have room for 2 electrons. Each orbital, each apartment here can only hold 2 electrons. No more, no more. It can hold 0 or 1 or 2. So when you're going through and filling in this off-bound diagram, let's say we want to fill in this for carbon. Carbon is right here. It is number 6. So it has 6 protons. It has 6 electrons. We know that there's going to be 6 electrons here. So we're going to fill in this off-bound diagram based on its rules. The first thing we're going to do is fill in 1s. So it's going to be filling in with 1s. That's going to be our first one. Now we have 1 electron at the first level, and we're going to have it be spinning up. By convention, we usually just say the first one in the room is the one spinning up. Then the second electron comes in. It does not want to move the stairs, so it has to be here. There's no other rooms on the first floor, so it has to be a roommate, and it's going to be spinning down. So that's going to be our first 2 electrons. Our third electron sees that first is filled, so it's going to move up to 2s and then fill up here. Then the next electron is going to move up. It doesn't want to have to walk all the way down the hall to the 2p block. Instead, it's going to fill in with 2s. Then the fifth electron is going to come in and fill in one of the rooms in the 2p block. The sixth electron is going to come in and fill in another empty room in the p block. So here we can say that this electron configuration is 1s2 because there's 2 electrons in the 1s room, the 1s orbital, 2s2 because there's 2 electrons in the 2s orbital, and then 2p2 because there's 2 electrons in the 2p block. If you wanted to go through and actually memorize and draw this off-bound diagram, that's one way, but then you have to kind of memorize this order, 1s, 2s, 2p, 3s, and kind of build this, which can be a little confusing. Another way, I know what a lot of people do is use this method. So if you go through, you can write out 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and write this out, kind of adding the next orbital down the line with each go. And then you can draw kind of this little diagonal rule and follow it along. So 1s2 goes to 2s2, goes to 2p6, to 3s2, to 3p6, to 4s2, and so on and so forth. This is a mighty fine way of going about it. I know a lot of people really do like using this when writing out their electron configurations, and that's fine. You can do it that way if you like, but I find it much easier to use the ultimate cheat sheet of periodic table. If you can just remember, this is ptable.com. If you go to the orbitals section, then you can find this. So you can see that this block here is going to be your S block. Elements here are going to have their last electron in the S block. And we know that if it's the first energy level, so these two are going to be 1s1 and 1s2. Okay. Here, we know that this is still in the s block, so it's going to be, the electron configuration is going to be 1s2, 2s1, because it's the first one in this 2s block. Over here, this is your p block. This is those dumbbell-shaped orbitals. And if I wanted to look at fluorine, we could go through and see that it's 1s2, 2s2, 2p, 1, 2, 3, 4, 5. So this is 2p5. There are 5 electrons in that p block now. This is going to be your d block. These are all your d orbitals. With the d orbitals, remember that these guys are shifted down 1. Why are these guys shifted down 1? So if we go back to our OffBound diagram, you can see that if you go up here, 3sp, then you fill in 4s, then you fill in 3d. So why do you do that? What is the reasoning behind that? The analogy that I like to use is sometimes it's easier to go up one more flight of stairs than walk 300 feet down a hallway, which is kind of what you're doing. You're kind of walking up 3 flights of stairs and then walking over 300 feet to get to this next block of apartments. You could just go up one extra flight of stairs, which is a lot easier, which makes 4S a little bit more of a prime real estate than 3D. Why is it that way in non-allegorical terms? It's because 4S is actually just a little bit more stable than the 3D. When you start getting into d orbitals, these are just a little bit more unstable than your 4s orbitals. These guys are just spheres. They're going to spend the vast majority of their time kind of closer together, closer to the nucleus, whereas these guys have, sometimes they're really close to the nucleus and sometimes they're further apart. So they're just, you have more variability. So 4s in general is more stable, whereas these guys are less stable. 4s fill in first. The last thing we have are the f orbitals down here. This is going to be your f block. So this is your f block. Your f block, very much like your d block, it is shifted down. So instead of these guys being 4, they're actually 3, because it's shifted down 1. With your f block, these guys are shifted down 2. So this first row here, even though it says that we're in period 6, these guys are all energy level 4. You can even see up on the screen the 4F13 for thulium down here. I would suggest using whatever method works for you. I've given you a couple of different methods, but I would highly suggest looking at and trying to remember the P block, D block, S block, and using this to go out and write your electron configurations. So let's talk about some weirdness with these rules. One of the first weirdnesses I'm going to talk about is when it comes to these noble gases. Sometimes you can do a kind of a shortcut. So what kind of shortcut am I talking about here? All of these are going to end with something P6. So neon is going to end with 2P6, argon 3P6, krypton 4P6, so on and so forth. These are very, very stable. And because of that, we can kind of use them as a starting place. So if I was going to go through and write out rubidium, I could either go through and write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. That's a lot. You don't have to do that. What you can do is use the noble gas abbreviation, which for that, what we do is we would write out the noble gas that precedes rubidium. So if you look, that would be krypton. So I would just write in brackets the symbol for krypton, Kr, and this is kind of an abbreviation for all the electron configuration for krypton, which is the vast majority of the electron configuration for rubidium. The only difference between krypton and rubidium is this last little bit, the 5s1. So we say it's krypton and then 5s1. Krypton 5s1. That is a good abbreviated version of this. So we've done the abbreviations. The only other weirdness is some weird exceptions to this rule. D orbitals are, like I said, a little more unstable, but they want to gain some stability. One thing that is definitely true is that a half full block is going to be more stable than if it's not full. We want to have that last block, that last room full. So sometimes if we have this like vanadium here, vanadium has 3d3. These three rooms, these three orbitals have one occupant in them. Now for chromium, what you would assume is it would be 3d4. 4s2, 3d4. The next one gets full. But once you do that, you can see that yes, 3d4 is full, but we also have 3d5. Where did that guy come from? That guy came from 4s. Now this is 4s1, 3d5. We've remember how I said you don't really like roommates, so we found that this configuration is just more stable, where you steal that 4s away and to get half full with 3d. With 3d5. Now half of these are full. This guy doesn't have a roommate anymore, so he's a little bit more happy. That happens. So this is going to be happening in group 6. Within group 6, with all of these guys, this is why some of these guys have weird properties. Chromium doesn't really have anything weird, but tungsten definitely has some very interesting properties to it. The other thing that happens here is going to be at the very end. It's a very, very similar situation where nickel is 3d8, and you would assume copper to be 3d9, but does the same thing. It steals an electron away from 4s1, or from the 4s orbital. Now it's 4s1 and 3d10, filling up that entire orbital. So we have copper, silver, gold, all those nice precious metals being even more stable now. And then zinc, cadmium, and mercury are just filling in that 4s2 electron. Those are going to be the only weirdness when that comes with electron configuration. Hopefully that was a good review for you guys. I think that was a pretty good review on electron configuration. If you have any more questions or anything, please send me a message or comment. Again, I'm going to be posting some assignments down below for my students. If you're not some of my students, welcome. I know it's a crazy time, and a lot of people are looking for help with their AP studies. So welcome. If you have questions, let me know, and I'll try to help you as best I can. All right, guys, I will see you next time. Have a good one.